Greetings, everyone. Learning is a hobby here. I want to go over Chapter 10 of Spivak's Calculus book, fourth edition that we've been going through. This is my chapter summary for Chapter 10. Let me bring up my notes and we'll go over everything. Um, in the previous chapter, we talked about the definition of the derivative, and here we're going to learn how to calculate the derivative. So, um, that's what he says here in the beginning. In this chapter, we'll derive formulas that'll allow us to differentiate a large class of functions without having to use the limit definition from the previous chapter, which, as we saw, if you looked at those videos or if you've tried the chapter yourself, you'll have noticed that it can be quite laborious. All right, so we have a bunch of theorems here to go through. Theorem one says if f is a constant function, so in other words, f of x equals c, then f prime of a is 0 for all real numbers a. And we just take the limit of the difference quotient and show that we get 0 from that, which you can look at here. We actually did a couple of these in the previous chapter, but now we're writing them down as formal theorems. Theorem 2, if f is the identity function, in other words, f of x equals x, then f prime of a equals 1 for all real numbers a. And again, to prove this, we just take the limit of the difference quotient at a, um, and see that we get the limit equal to 1. All right. Again, that's another example that we did in the previous section, but again, we're writing it down here as a formal theorem. All right, theorem 3, if f and g are differentiable at a, then f plus g is also differentiable at a, and f plus g prime of a is just the sum of the derivatives of f and g evaluated at a. And again, this is just an application of definitions here. F plus g prime of a is the limit as h goes to 0 of f plus g of a plus h minus f plus g of a, all divided by h, which is the same thing as limit as h goes to 0 of f of a plus h plus g of a plus h minus f of a minus g of a all over h. And then we could just rearrange some terms here. That's equal to the limit h goes to 0, f of a plus h minus f of a plus g of a plus h minus g of a all divided by h, which is the same thing as the limit of f of a plus h minus f of a all over h plus g of a plus h minus g of a all over h. And then we could distribute the limit. And that gives us that the derivative of f plus g of a is f prime of a, or the derivative of f at a plus the derivative of g at a. Okay, next theorem is the product rule. If f and g are differentiable at a, then f times g is also differentiable at a, and f times g prime of a is f prime of a times g of a plus f of a times g prime of a. And here's the proof. This just involves a little bit of a trick. If we take the limit of the difference quotient as h approaches 0, then we get limit h goes to 0, f times g, a plus h minus fg of a all over h, which is the same thing as limit h goes to 0 of f of a plus h, g of a plus h minus f of a, g of a over h. That's, just from the definition of the product function. And that's equal to limit h goes to 0, f of a plus h, g of a plus h, minus f of a times g of a plus h, plus f of a times g of a plus h, minus f of a, g of a. The trick here is to add 0 in a convenient way. So if you notice, the sum of these two things adds to 0. So it's not like we're changing the value of anything by um, adding and subtracting that quantity from both of the terms. All right, but the reason that we're doing that is because we get, when we can rewrite this over now in a more convenient way. That's equal to the limit h goes to 0 of f of a plus h minus f of a all over h times g of a plus h plus f of a times g of a plus h minus g of a all over h. And then you could, again, distribute the limits. And when you take the limit, you get the product rule. All right. Theorem number 5 is a special case of theorem number 4, where g of x is a constant times the function f of x. Sorry, g of x is a constant times f of x, and f is differentiable at a. Then g is differentiable at a, and g prime of a is just a constant times the derivative of f at a. All right, and you just apply the product rule that we that we talked about up above, and you get the formula. So I won't really go into that into detail there. You can see it yourself. Here's a note by theorem 5, negative f prime of A is negative f prime of A, which implies that f minus g prime of A is f prime of A plus the negative of g prime at A, which is f prime of A minus g prime of A. So the formula works for differences as well. All right, theorem 8 is the power rule. If f of x equals x to the n for some natural number n, then f prime of a equals n times a to the n minus 1 for all numbers a. And we actually proved this in the last chapter, but we did it a slightly different way that not slightly we did it a different way than we're doing it here. So we'll proceed by inducting on n. So the base step n equals 1 is just theorem 2, so we don't have to show anything for that. The inductive step, assume x to the n prime is n x to the n minus 1 for some natural number n, and consider x to the n plus 1. Then x to the n plus 1 prime, or the the derivative of x to the n plus 1 equals the derivative of x times x to the n, which by the product rule is x prime times x to the n plus x times x to the n prime by theorem 4. And that implies that x to the n plus 1 prime is 1 times x to the n plus x times n to the times x to the n minus 1, which, and if you simplify and factor out the GCF, you get 1 plus n times x to the n. So that shows that the theorem holds for all natural numbers. Okay, we have another note here. With all the above theorems, we're now capable of differentiating any polynomial. A polynomial is a sum of the form, aj, j going from 0 to n. The first derivative is just aj, j times x to the j minus 1, summation where j goes from 1 to n. If you take the kth derivative, you get this polynomial here, summation j equal k to n, aj, n factorial over n minus j factorial, x to the n minus k. That's if k is less than or equal to n. And for all k greater than n, the derivative is 0. Right, theorem 7, if g is differentiable at a and g of a is not 0, then 1 over g is differentiable at a, and 1 over g prime of a is negative g prime of a over g of a squared. Here's our proof. We have to take care of a technicality before we get to the limit of the difference quotient. Since g is differentiable at a, g is continuous at a by theorem 9.1, and g of a not 0 implies 1 over g of a plus h is defined for all h in some delta neighborhood around a, for some positive delta, by theorem 6.3, which is this theorem here. Suppose f is continuous at a and f of a is greater than 0, then f of x greater than 0 for all x in some interval containing a. More precisely, there's a number delta greater than 0 such that yada, yada, yada. And similarly, if f of a is less than 0. So this is a theorem that we proved all the way back in chapter 6. If you want to, look at the whole chapter 6, you can go back in my videos to see that. Okay, so now that we've established that we don't have to worry about 1 over g of a plus h being defined for some, arbitrarily small values. Now we can proceed. 1 over g prime of a is equal to the limit of the difference quotient, which is equal to limit h goes to 0 of g of a minus g of a plus h over h times g of a times g of a plus h by just, simplifying. And then just rearranging some things, that's equal to limit h goes to 0 of minus g of a plus h minus g of a over h divided by g of a times g of a plus h. And then distributing the limit on top, we get the negative of the derivative of g at a. And in the bottom, because g is continuous, we get g of a times g of a, which is g of a squared. All right, theorem 8. If f and g are differentiable at a and g of a is not 0, then f over g is differentiable at a, and f over g prime of a is equal to g of a times f prime of a minus f of a, g prime of a, all over g of a squared. This is called the quotient rule. All right. So here's the proof. Take the limit of the difference quotient. Sorry, not we don't have to use the definition here. Take the we can write f of g f over g as f times 1 over g, and then just use the product rule and the previous theorem. So you just get what you need when you simplify everything at the end. Okay, we can now differentiate an even larger class of functions, and Spivak goes through some examples here. I won't do this in detail because we're going to do, a lot of problems from the exercise set, but you could, see here and get some practice with these functions if you haven't seen the quotient rule before. All right, I will actually look at part C though. F of x equals 1 over x. If you take the derivative of that using the quotient rule, you get negative 1 over x squared, or in other words, negative x to the minus 2. Uh, this function actually can be this derivative of that function can be generalized if n is any natural number and f of x is x to the minus n, or in other words, 1 over x to the n, then f prime of x by the quotient rule simplifies to give you negative n x to the minus n minus 1. So theorem 6 holds for all integers not 0. Furthermore, if we interpret f of x equals x to the 0 power, to mean f of x equals 1, and f prime of x equals 0 times x to the minus 1 to mean f prime of x equals 0. We say interpret because it's not clear how to define 0 to the 0, and 0 and also 0 over 0 is undefined. Then theorem 6 holds for all integers n. So the power rule holds for all integers. All right, he gives us the derivatives of the two main trig functions, but he doesn't prove it here. We're going to do that in a later chapter. There's a whole chapter on trig functions. But he gives us the derivatives here. So the derivative of sine at a is cosine of a, and the derivative of cosine of a is negative sine of a. With the above facts and all the previous theorems, we can differentiate many new functions. Again, Spivak goes through a bunch of examples. You can try them yourself. I'll just scroll through these because, again, when we get to the exercises, we're going to do a lot of problems. But you can get the idea by practicing with these. And just to remind you guys also, I always upload the PDFs for the chapter summaries and my exercise solutions to the Patreon page, which is $3 a month, and you can download all that stuff, as many times as you want for $3 a month. Okay, so you can look at these there if you want to, or you can pause your screen. Another note here, notice that h prime of x plus g prime of x equals 0, as well as h double prime of x equals g double prime of x equals 0. Here he's talking about, so g of x is sine squared, and h of x is cosine squared. So if you take the derivative, the sum of the derivatives, you get 0, and the sum of the second derivatives, you get 0, which shouldn't be surprising since the sum of the two functions at x is cosine squared x plus sine squared x, which if you remember from trigonometry is always equal to 1, and the derivative of a constant function is always 0. So, okay, another note, a function involving triple products can also be handled by theorem 4 in two ways, using associativity. So f times g times x prime. If you notice, you get this nice symmetric formula for the derivative of the product here. You take the derivative of f times g times h plus f times the derivative of g times h plus f times g times the derivative of h. And if you notice, you get the same thing if you associate the other way, right? And then we have some examples here. Again, I won't really go through this in detail because you can pause your screen and try it, which you should. But again, we're going to be doing a bunch of problems later on. So um, Spivak does mention this proposition here in the chapter. If f, g, h, k are functions that are differentiable at a, then if you take the derivative of, sorry, there should be a prime here. If you take the derivative of the product of those four functions at a, then you get a similar formula for the product of three differentiable functions. He asks you to prove it. I skipped it just because we proved the general case in a second. So there's no point in proving that one since we have the general case down here. And again, Spivak doesn't actually prove this in the chapter. He asks the reader to do it. So this is my proof. Uh, let's say that we have a set of functions f sub I, where f sub I is differentiable at, sorry, this should be at a, for I be for I between 2 and n, then the product of all those functions, if you take the derivative of them at x, you get, the formula that you would expect. So let's show that this works by inducting on n. The base step is just theorem 4, so we don't have to show anything for that. The inductive step, assume that the derivative formula holds for some natural number n, so a product of n functions, in other words, right? For n greater than or equal to 2, then consider the product of n plus 1 functions. That's the same thing as f n plus 1 times the product of the fi's, where I goes from 1 to n. And then by using the product rule and the inductive hypothesis, we get f prime n plus 1 times the product function of the fi's, where I goes from 1 to n, plus fn plus 1 times the derivative of the product of I going from 1 to n, which is given by that summation. That's the inductive hypothesis. But if you notice, when you simplify everything there, you get the formula for n plus 1. So that works by induction. All right, theorem number 9, which is the last big differentiation rule here, which is the chain rule. If G is differentiable at A and F is differentiable at G of A, then F composed with G is differentiable at A, and F composed with G prime of A equals F prime of G of A times G prime of A. And in order to do the proof formally here, we actually have to make a definition and prove a lemma. So let's define this function. You'll see why we're doing this in a minute or so. Define the function phi of h to be f of g of a plus h minus f of g of a divided by g of a plus h minus g of a, if g of a plus h minus g of a is not 0, and define it to be f prime of g of a if g of a plus h minus g of a is 0. Okay, and then we're going to prove a lemma about that function phi. Phi is continuous at 0. Right, and here's the proof. Since f is differentiable at g of a, the limit as h goes to 0 of f of g of a plus k minus f of g of a over k is equal to f prime of g of a. Also, g is differentiable at a, so g is continuous at a. That was theorem 9.1, if you remember. Then for any epsilon greater than 0, there's delta greater than 0, such that for any h real number, absolute value h less than delta implies that absolute value g of a plus h minus g of a less than epsilon. Also, by the first limit, meaning this one here, for any epsilon greater than 0, there's delta prime greater than 0, such that if k in absolute value is greater than 0 and less than delta prime, then the absolute value of f of g of a plus k minus f of g of a over k minus f prime of g of a is less than epsilon. Right? Then take delta hat greater than 0, so that the absolute value of g of a plus h minus g of a less than delta prime when absolute value h less than delta hat. Then for k, let's call k equal to, really this should be a function k of h, but I'll just leave it as k here. K equals g of a plus h minus g of a. Assume that that's not 0. Then we have the absolute value of phi of h minus f prime of g of a is equal to, here when you expand phi of h, you get f of g of a plus g of a plus h minus g of a. That's the same thing as f of g of a plus h, but we're writing that in that specific way because we want to use what we showed up above. Minus f of g of a all over g of a plus h minus g of a minus f prime of g of a. Notice that that's the same thing as absolute value f of g of a plus k minus f of g of a all over k minus f prime of g of a, which is less than epsilon. Therefore, the limit as h goes to 0 of phi of h equals f prime of g of a, which is phi of 0. So that means that phi is continuous at 0. All right, continuing now with our proof of the chain rule, now that we have all that stuff about phi. F of g of a plus h minus f of g of a over h is the same thing as f of g of a plus h minus f of g of a over g of a plus h minus g of a times g of a plus h minus g of a over h. All we did was multiply the top and the bottom by g of a plus h minus g of a, which is equal to 1, so that doesn't change the value of anything, provided that G of A plus H minus G of A is not zero, right? That's equal to phi of H times G of A plus H minus G of A over H. For all H not zero, even when G of A plus H minus G of A equals zero, since in this case, uh, on both sides you get zero if that's the case, if that expression goes to zero, right? Because zero equals f of g of a minus f of g of a all over h, right at the top there is always zero, equals f prime of g of a times zero over h, which is again is equal to zero. So therefore, F, now we can actually prove the chain rule here. F composed with G prime of A is equal to the limit of the difference quotient, which is equal to the limit H goes to zero of phi of H times G of A plus H minus G of A over H, which is equal to, here I just distributed the limit, and the limit of phi of H as H goes to zero is F prime of G of A. By the way, we defined it, and the limit of G of A plus H minus G of A over H is G prime of A, and that proves the chain rule. Okay, so that's kind of an involved proof, but Spivak spends some time explaining why we have to do it that way. The above proof is necessarily uses the function phi, since otherwise we have to deal with the difficulty that g of a plus h minus g of a might be zero for arbitrarily small h. In a case like this, we can't simply write, what we want. In other words, we can't just divide and multiply by g of a plus h minus g of a because um, G of A plus H minus G of A might be zero for an infinitely small H. All right, an example of such a non-constant function would be, for example, g of x equals x squared, sine of 1 over x, x not zero, and 0 of x equals 0 for x values close to 0. So just so it's clear that actually this is something that we do have to worry about. So okay, then we give Spivak goes through some examples of using the chain rule to differentiate functions. Again, I won't really make a big deal about this. You can pause your screen or you can go to the Patreon page and download the PDF, or you can just do them in the book yourself. Um, Notice that in the cases where we use the chain rule here, it matches with, if there's another way of doing it, like with the product rule, like we have in part B. Notice that the two rules actually agree with each other, which is good. All right, just going through these examples. Like I said, I'm not going to go through this in detail. You can pause your screen. Here's a note. In general, if a function is multiply composite, so if you have a composition of, let's say, n functions, then you can reassociate in the way that I have written here. And then what you do, just to be systematic, is you differentiate from the outward, going from outward to inward, right? And then lastly, in the exercise set, Spivak says we'll be asked to prove that these properties of these two functions that we have here, if f of x is x to the 2n sine of 1 over x for x not 0 and 0 if x equals 0, then the first order derivative all the way up to the nth order derivative of 0 exists, but the nth order derivative of f is not continuous at 0, whereas if f of x is x to the 2n plus 1 times sine of 1 over x, x not 0, 0 if x is 0, then the first through nth order derivatives at 0 exist, and the nth order derivative of f is continuous at 0, but the nth order derivative of f is not differentiable at 0. So I assume that means that there's an exercise or two that deals with this, when we get around to it. Okay, last thing for this chapter summary, is a note. The above example suggests that quote unquote reasonable functions can be characterized by the possession of higher order derivatives. No matter how hard we try to mask the infinite oscillation of sine of 1 over x, this behavior is revealed by a derivative of sufficiently high order. Unfortunately, we'll see later that even worse things can happen. Lastly, it seems tempting to write some of the theorems in this chapter. Actually, I sort of abuse notation like this just because it's so much more convenient to write it this way. But it can be tempting to write some of the theorems in this chapter as equations about functions rather than about their values. So, for example, f plus g prime is f prime plus g prime, et cetera, et cetera. Strictly speaking, these equations may be false because the functions on the left-hand side might have a larger domain than those on the right. However, if f and g are differentiable everywhere in their domains, then these equations and others like them are true, and this is the only case that anyone cares about. All right, and that's chapter 10. Let me stop my screen share. So there is a pretty long exercise set for this section. I haven't really looked through it yet, so once I decide what problems I'm going to do and write up my notes, I'll make the video for that, which should be out sometime this week, I'm hoping. So again, thanks for watching, everybody. Give me a like and subscribe if you enjoy this content. Let me know what you think down below, and take a look at the Patreon page if you want access to the PDF files. And I'll see you guys in the next video.